So welcome everyone, and this is the session on real-world applications. My name is Nava Tintarev, and I'll be your chair for the session. As many of the other sessions, you'll know that you can ask questions in the WUVA agenda entry for a particular presentation. If you're in the desktop app, the live streaming video should be playing in a floating window so you don't miss anything. As you know, we have a tight schedule, but please do take advantage to follow up with the speakers and continue the discussion on WUVA if we don't manage with the Q&A questions we get posted. So without further ado, I'd like to get started with our first speaker. This is Pigi Kouki, and she'll be talking about the home improvement domain and in particular session-based recommendations. So take it away, Pigi.
Thank you. Can you see my screen?
Looks good.
Okay. Hi, everyone, and thank you for attending my talk. Today, I will present our paper on session-based recommendations for the home improvement domain. This is joint work with my colleagues from RelationalAI, the Home Depot, and HyperCube. Our work is motivated by two different lines of research. In the first case, there is a multitude of algorithms for session-based recommendations. These algorithms range from simple k-nearest neighbor approaches to complex deep learning architectures. However, the evaluation of these models is based on offline evaluation metrics only and is using different datasets. At the same time, very recent research showed that baseline models, when carefully tuned, can outperform deep learning models in a variety of metrics. In the second line of research, there is a lot of discussion around the fact that offline evaluation is not enough. This is true especially for the home improvement domain for the following reason. Offline evaluation penalizes an algorithm if the recommended product is not exactly the same with the product ID in the ground truth. However, it is usually the case that there are near identical products that they should be considered as equally good recommendations even if they do not share the same product identifier. Let's give an example to showcase the shortcoming of offline evaluation metrics. Assume that there is a user that has a fridge and a microwave in the cart, and we know from historical data that the next item that will be added to the cart is a microwave. Also assume that three different algorithms came up with three different recommendations. Algorithm A recommended a microwave that is very similar to the microwave added to the cart. Algorithm B recommended a kitchen stove, while algorithm C recommended a kitchen sink part. For a human, when looking at these recommendations, it is easy to understand that there are multiple levels of relevancy. A recommendation of algorithm A is more relevant compared to the recommendation of algorithm B, which is more relevant compared to the recommendation of algorithm C. However, when applying traditional evaluation metrics, all these recommendations will be considered as equally bad because none of the IDs of the recommended products matches exactly the ID of the product added to the cart. So, given the above discussion, when it comes to a large e-commerce application such as the Home Depot, it's not straightforward to know what is the best session-based recommendation algorithm to put into production. First, because there are so many models that we can choose from, and second, because the offline evaluation is not enough to make an informed decision given the peculiarities of the domain. In this paper, we describe the journey of the Home Depot towards finding the best session-based recommendation algorithm. Our evaluation is divided into three parts. In the first part, we evaluate the performance of 14 different models in a variety of metrics and distinguish the top 5. In the second part, we use those 5 models and perform an additional round of evaluation using human experts to account for different levels of relevancy. In the third part, we use the best model from the previous part and perform an A/B test that showcases the improvement in business metrics that the Home Depot was able to achieve as a result of our work. Now let's discuss the different parts, starting with the offline evaluation. We evaluated the performance of 14 different models designed for session-based recommendations. 8 of those models were baselines, while 6 of them were deep learning architectures. We report the performance for each model in a variety of metrics, ranging from the ability of the model to evaluate the immediate next item to add to the cart, to the ability of the model to evaluate a list of items that will be added to the cart. Additionally, we report results on coverage and popularity. We retrieved add-to-cart actions for 3 categories that get a lot of traffic in the Home Depot. These are outdoors, tools, and appliances. For all models, we perform hyperparameter tuning using a validation set. Here, we will present a subset of the results for the offline evaluation. The graph shows the performance of the 14 different models for the outdoors category in terms of predicting a list of items and in particular precision at 5. For this metric, a baseline model called VSTAN statistically significantly outperforms all other models, including all deep learning models. When evaluating the ability of the models to predict the immediate next item, here we report hit rate at 5, then a very recent graph neural network called SRGNN is the best option. And finally, when it comes to coverage and popularity, VSKNN, a baseline model, and GRU4Rec, a deep learning architecture, seem to be the best options. The result of this offline evaluation is that not a single model outperforms all others in the accuracy metrics. So we selected the 5 models that perform the best to participate to the second round of evaluation. In this second part of the study, we trained all 5 models using the same data and generated predictions for the same real sessions. Then, we asked human experts from the in-house validation team of the Home Depot to give us labels. Now let's discuss the design of the experiment. Validators were shown 2 sets. The first set consisted of the items that the user has in the cart, and these were the items that each of the 5 models used in order to come up with the predictions. The second set we showed the items that the user added additionally to the cart, which was considered our ground truth. For each model, we generated the top 5 recommendations. For each recommendation, we asked the validators to give 1 out of 3 available labels: thumbs up, check, and thumbs down. A recommendation was considered as thumbs up, which we call objective relevant, if the item recommended was exactly the same or very similar to one of the items added to the cart. In this example, the says long here is very, very similar to the says long in the ground truth. So despite the fact that the 2 products do not share the same ID, the recommendation is considered as objective relevant. A check was assigned to recommendations that were not objective relevant, however, they made sense given the items currently in the cart. For example, an ottoman is not in the items that will be added to the cart next. However, given the fact that the user has added to the cart a swivel, then it makes sense for the system to recommend an ottoman. Finally, recommendations that were irrelevant to the items currently in the cart and items in the ground truth were assigned the thumbs down label. For each recommendation, we got labels from at least 3 different validators. Since we asked the validators to use their critical thinking, there were times with disagreement. To resolve the disagreements, we applied a majority vote algorithm. This was a large experiment. We got around 35,000 labels, about around 1,000 different sessions. Here are the results for the objective relevant metrics for all categories. The model that statistically significantly outperformed all others is GRU4Rec. We note here that we did not choose GRU4Rec to participate to this second round of evaluation because of its great performance in terms of accuracy metrics, but because of its great performance in coverage and popularity. The results for the subjective relevant metric show that another deep learning model, STAMP, performs the best. Similarly, STAMP did not outperform in any of the accuracy metrics in the offline evaluation. It was chosen to participate to part 2 of the study because it performed decently in terms of accuracy, and at the same time, it showed satisfactory performance in terms of coverage and popularity. In this slide, we compare the performance of the algorithms in part 1 and part 2 of the study. To this end, we plot precision at 5 from part 1, along with the objective relevant results from part 2. The conclusion is that the ranking of the algorithms from the offline evaluation does not agree with the ranking of the algorithms from the human evaluation. For example, VSTAN, that was the clear winner in terms of precision in the offline evaluation, ranked in the last position in the evaluation using human experts in 2 out of 3 datasets. If we look closer to the comparison between baseline models and deep learning models, we observe that the baseline models rank in the last positions, suggesting that for the home improvement domain, deep learning methods seem to be more appropriate because they can probably capture deep interactions between the items that simple methods are not able to do. Finally, in this graph, we plot the percentage of recommendations that were assigned the label thumbs up by the validators. This is the objective relevant. However, the ID of the recommended product did not match the ID of the product in the ground truth. This happened with the example of the saislong that we described a few slides ago. In other words, this percentage shows how often an item should be considered as relevant because it is very similar to the ground truth. However, all offline evaluation metrics cannot capture this fact because they need exact ID match between the recommended and the ground truth item. Interestingly, this percentage is very high for all algorithms. It ranges from 6% to 21%. This shows that offline evaluation metrics cannot capture a very large number of recommendations that are indeed very relevant and very close to the ground truth. As a result of the second part of the study, we had to choose only one model to move to the A/B test. We decided to go with STAMP since it performed the best when summing the scores in objective and subjective relevance. So let's discuss the design and results of the A/B test. The treatment was the STAMP model, while the control was a third-party leading solution that the Home Depot has in production. We ran an A/B test for 2 weeks with 50-50 split in the full traffic. The results are as follows. Conversion rate increased by 15.6%, while revenue per visit increased by 18.5%. To summarize, in this work, we studied the performance of a set of models for session-based recommendations for the home improvement domain and performed 3 different evaluation procedures. We hope that our lessons learned towards finding the best session-based algorithm for our application scenario can be helpful to researchers in industrial and academic settings. Finally, we would like to note that our findings showed one more time that offline evaluation is not enough in the session-based recommendation scenario. An important lesson learned is that experiments with real users are needed to better understand how its method performs. Thank you very much, and I will take any questions.
So thank you, Pigi. Indeed, we have some time for questions. Remember that you can use Huova to post these. I'm looking here in the chat. How many experts did you use in the human expert evaluation stage? This is a question from Shujun.
Yeah, I think there were 10 experts.
10 experts. And then a question from Mustafa. Do the experts also see characteristics of items such as brand, price, quality, or do they only judge based on the images?
Yes, that's a very good question. So yes, they had access to the image, access to the product title, product description, and they were also provided with a link that showed the Home Depot product page for this product. So if from the image, title and description, they were not able to make an informed decision, then they could go to the product page in the website and see all the details of its product.
There's lots of questions here. I'm thinking which ones we have time for. From Juan, how many samples for each category do you use in the human expert evaluation?
We had three different categories and around 10,000 sessions. So it was around 3,000 per category, 3,000 something.
And a very interesting question from Vincent. How do you handle out-of-stock items? Do you shift the recommendation or do you look for a substitute?
For discontinued, so for this study, we have filtered out all discontinued products. Out of stock. This was not so the human expert evaluation was done offline. So we didn't account for out of stock products.
That's fair enough. From Dennis, why did you need to choose one method rather than creating and use ensembles, considering the strengths and weaknesses?
Yes, this is a very good question, and this is in our future work. For A/B test, it was already very, very complicated to put a deep learning model into production to serve millions of customers with very low latency. So it was already challenging. But given the fact that different models have different advantages, then in our future work, we would like to experiment with ensembles.
Nice. And here's a question from Fernando. I guess he's asking here whether the deep neural methods here are applied directly to the images.
No, so for this study, we used only sequences of items of real sessions and no textual information, no images, nothing. Just
the IDs.
Yeah, exactly.
I think we can manage one more and then encourage people to move on to Huva. Does your work suggest any possible offline evaluation metrics that could be designed to measure, optimize the desired behavior? It might not be always possible to get so many expert labels.
Yes, again, this is a very nice question. In our future work, we are planning to do this in an automated way. We're planning to use textual information and image information to generate similarities between products, and then don't ask directly human validators, but see if the similarity of the product in the recommendation list and the product in the ground truth is above a threshold that we will compute that, and then we will accept this as relevant recommendation.
So thanks again, Pigi, for the very nice presentation. Our next speaker is Tio, and he'll be talking about seat recommendations. So if you share your screen.
Yes. Yes, I think that's okay. So,
looks good.
Hi everyone. Thank you. Is that good? Yeah. Can you hear me? Does everyone hear me now? Okay. So, hi everyone. Thank you for being virtually here for the presentation of my work done during my research master in collaboration with my supervisor, Daniela Louise and Simon Blanchard. So the title of our paper is a bit long, but the end can summarize the topic we'll discuss here, which is seat recommendation at reserved seating venues. Okay, so our problem is the following. When a customer buys a ticket in a venue such as a theater like the Saint-Denis Theater represented here, what location will he choose? So let's start by a summary of what drives a customer in his decision. So the first observation that can be made is that the choice will depend on the location of the seat of the room. For example, sit at the front rather than sit at the back, etc. And so among the factors to consider, the position of the seat is essential. But that's not all. As over time the room fills up, some seats have to be updated to become occupied. But also the available seat may become less attractive if they are surrounded by unavailable seats. And therefore, proximity to others is also a factor to consider here. And finally, one last thing that can be said is that these preferences are personal, and the importance of this factor can be very heterogeneous from one customer to another. So based on this remark, how can we model our problem? And so we can sum up with two different points of view. The first one is the traditional classification approach. We have partially filled room for input, and the class here are the available seats, and we use a classification algorithm to find the most attractive ones. Doing so allows the exploitation of data from all customers to model high-order interaction with an algorithm that would have a high capacity, for example, with neural networks. But on the other hand, customers are not distinguished, and the information of each behavior will be lost because the data is concatenated. The second solution is to treat each customer individually and thus make a recommender system. Doing so allows the capture of difference in behavior, but individual level modeling performance also tend to suffer when customer data is sparse. Only a few or no past purchase in the borderline case of the core style problem where a customer without history, the customers don't have any history in the venue. So which of the two point of view is the best? Is it the one that process all the data together or the one that distinguish each customer? In our paper, we argue that the two approaches are complementary in the information provided for the prediction. The first component can focus on high-order interaction between seats, while the second one only use one customer history to consider personal preferences. And so combining them allows us to be more flexible for customers for which the model's user has little or no data. So here's a diagram representing the overall architecture of our approach. So from a database of ticket purchase data from one or more rooms, we pre-process it to have it in the format we want. And then the architecture is divided in two with an individual level part, which is here the upper part, calculated for each customer separately if we have enough data. Here I write 5 as an hyperparameters. And on the other part, the deep part, which is computed for without any customer distinction and can use all the data. And then the two methods provide two different seed prediction and are merged to obtain our final prediction. So let's successively describe the individual level part and the deep one before looking at how we can combine them. So first of all, the individual level part, which is a choice-based model with estimation by machine learning. So in other terms, we have 3 steps for these components. The first one for each seat J that are available in every room where a customer I choose a seat, we compute a set of feature Fij based on position, proximity to others, etc. Then we introduce Yij, a binary variable that indicates if the customer I choose the seat J. And finally, we train a binary classification model to estimate the probability of the seat J to be chosen by I. And various algorithms can be tried, like SVM, random forest, GBT, etc. For the deep component, we have all the aggregated data, and therefore we can use an architecture that requires more data. And so the problem here is seen from a multi-class classification point of view with 1 seat per class. So the room is given as input in the form of a binary image to keep the geometry. And thus the architecture we use is a CNN with here 2 adaptations. The first one is due to the fact that the number of classes, which is the number of seats, is the same size as the input, which means that it can be seen as a reconstruction of the input. And so the architecture is similar to a CNN autoencoder. And the second modification is made to make the prediction only on the available seats and to assign a 0 probability to the occupied one. And it is done by applying a mask on the softmax output of the network. For the combination, it was important to do it differently for each customer. Because the performance of the model varied significantly. For example, the individual level component perform much less with a small history. And even if we consider clients with the same history size, some were much more predictable than others. And so we proceed to a convex combination of the 2 output vectors with a parameter alpha learned for each customer by gradient descent. And the sigmoid function is also applied before the gradient computation to avoid any problem of exploiting gradients. So 2 experiments have been conducted to validate our approach. In the first one, we use data from a work conducted by Simon Blanchard et al., who have collected choices of participants from a panel. Several datasets are created with different configurations, so varying the size of the room, the number of choice made per client, the room occupancy. etc. The detail of the results are obviously in the paper. The main thing to remember here is that the hybrid architecture outperforms all other methods, and in particular, its two components used alone, which gives evidence that the two components provide useful and complementary information prediction. For the second experiment, we obtained 12 years of ticket purchase data from a large North American concert hall. So the room is represented here. The size is 31 times 57, but each row doesn't have the same number of seats, so we add padding to make the input square. Using data from a real room added over challenges, including not having the same history size for all customers. But again, our hybrid architecture provides the best performance for prediction, which proved the flexibility of the model from the quantity of available data and also from the size of the room. So to conclude, we provide a solution to a problem that has been very little addressed in the past, whereas it could be used by the cultural industry to improve marketing strategies with revenue management or personalized recommendation. This solution is a hybrid method for recommending seats and is the state of the art by being more flexible on the amount of data available. And these results are confirmed with a real-world application, which is also a contribution. Thank you for your listening.
So thank you for the nice talk, Theo. Again, we're welcoming questions from Uva. I would also like to remind people listening that you can ask questions earlier. It gives me more time to read through them as well and to make sure that we're not rushed in the question session. While we wait for them to come through, a question for me maybe, do you feel that this is going to change a lot during Corona time where distance is obviously a big parameter increasingly?
Yeah, this is a funny question, but actually it can change, as if people used to consider how they are the proximity to others when they choose seats. Maybe the history is not that relevant now because of all the Corona, and so maybe it's gonna change like the behavior of everybody, and maybe the prediction will be harder now. So probably yes, probably.
Yeah, and a similar question in a sense from Oriol. Does the model consider seats with limited visibility, and how would you then encode these? So probably visibility of the scene.
I think we didn't encode anything about like the characteristic of the room, like where is the screen and everything, but it's more like which seats are preferred by customers. So maybe we'll have data, and by the seat that are more chosen, we can deduce that this seat is more attractive. And maybe it's because like the proximity of the screen or something else, like the visibility or the sound, but it's not directly encoded that the screen is in front of the room and or the visibility, etc.
But there's so you have some sense that some seats are more preferred than others, so you can use preference patterns indirectly.
Yeah.
It's exactly. Another question from David or David. There's also an interesting question from Vineth. Why you use CNN rather than RNN-based models where you might have a sequential pattern of the users?
That's actually, that's also a good question, because like you can see it as a sequence because you can see your room as something that fills up over time. So you have this sequential pattern. My architecture uses CNN because I want to keep the because of the geometry of the room, actually. Like the way I encode my room is a binary array with, for example, 0 if the seat is occupied and 1 if it's available. So obviously I can see it as a binary image and use a CNN. But maybe there's And I think it's something that can be done for future works, is that combining maybe CNN for the geometry and RNN for this recurrent part, because the room fills up over time. Maybe it's a way to improve the recommendation. Sure.
Yes. Some very pragmatic questions here from Zeno. One is, how many training examples did you need to train?
Okay, you can find all the details on GitHub and on my article, but it's varying. Like, there's multiple data sets, but on the first experiment, I would say I think it was something like 50K choices, like from something around 500 customers. And on the other one, there is more, but I don't want to say something. I don't remember.
Yeah. So I think that's the rest will unfortunately have to be discussed on Wova, but I can assure you there are many questions, so there will be a nice interaction following on. I'd like to invite now Jesus to share his screen, and this is a very cool augmented reality setup for comparing products. There's no audio. We need you to unmute yourself.
Sorry for this. Now it's fine, right?
Excellent.
Yeah. Hello, and thank you for the introduction. Again, my name is Jesus Alvarez. I am part of the Interactive Systems Group at the University of Duisburg-Essen, and I am here to present our research regarding in-store AR-enabled product comparison and recommendation. Nowadays, it is not uncommon for specialized stores to have plenty of different options for products of the same type. This can quickly become an issue if the client lacks the required knowledge for choosing one. And if we also consider that customers not always have well-defined preferences, they may suffer of choice overload and be incapable of making a decision with confidence. We know that recommender systems are suitable tools for addressing these issues. The problem is that they are mostly an online element, and especially in shopping scenarios, they rely heavily on many other online features, which could hardly be transposed into physical settings, or so was the case some years ago. Now that multi-channel retailing is a thing, and the different customer touchpoints are more and more integrated, physical retailing is slowly evolving into a new kind of experience. Special attention must be paid to augmented reality technology, which allows for the seamless integration of digital and physical worlds. Combining it with recommender systems has the potential for offering both an engaging customer experience and pragmatic benefits in terms of search and decision support. And in this case, we would be also combining physical and online retailing, which means that we can have the benefits of both worlds too. This constitutes the foundation of our approach to AR-based recommending at the point of sale. Now I will go through the main points of our concept and the implemented prototype that is based on it, which runs under Microsoft HoloLens and takes vacuum cleaners as the product domain. In our approach, the information appears anchored to the physical product. Hopefully, you can see now the prototype running in our lab. The part on the right side is for recommendations, but we'll leave that for later. The left side shows various categories and how well the product performs for each one of them. Tapping on a category grants access to the related attributes, and if we tap again on an attribute, we see related properties, its location in the product, and the description. The second point of our approach has to do with supporting attribute comparison, which is the most common practice when deciding between different products in a physical store. However, it has limitations concerning short-term memory demands, but luckily previous research indicates that this can be alleviated by using augmented reality. So in the prototype, users can select different products by tapping on them, and a color is assigned to each one of the selected ones. In this case, that's purple for the product that has been selected. When we move to another one, we can see which products have been previously selected. And if we select another one, like this here, the system will display the attributes in a side-by-side manner. We can do so with up to 3 products, and the functionality presented in the previous point is still available, so that it is possible to go inside categories and obtain more information. The method allows clients to move around and compare products that are far away one from each other. The recommendation part is built on top of this. The system provides recommendations for each physical product. It uses a content-based technique, which utilizes the attributes of the product currently in the user's AR focus for retrieving similar items. 2 similarity scores are calculated. The first one takes into account functional attributes only, while the second one is based on visual aspect. It has 2 components, one that takes visual-related attributes for its calculation, such as color or size, and another one that is based on image similarity. Both are combined to obtain the similarity score for the appearance. Finally, the system provides 4 recommendations, 2 of them for each similarity score. Now, taking a look to the prototype, this is how they are presented. A client can examine them, which is what the user is doing now. They can be removed, which brings a new item on its place. They can be also saved using the heart icon, or we can compare them just as we would do with a physical one. Regarding this, a recommendation can contain products that are physically present at the store, as well as others that are only digitally available. Lastly, attributes can be critiqued by users, which in turn generates new recommendations. This is done by tapping on these 2 little buttons that appear next to a selected attribute. In this case, for requesting items with a higher or lower weight than this one. Then a new rule is added and the recommended items are refreshed. Yes. So this is not the first attempt at AR-based shopping support or in-store recommendations. There are even a few instances where they have been combined already, like it is the case of Gutierrez et al. However, research in the area is still scarce and requires further exploration. Aspects such as the development of the client's preferences in this context, or the implications that having both physical and digital products may have in the client's decision-making process, are factors that have been generally overlooked due to how rarely these elements are presented together. We can extract our research questions from this concern. That is, how effective are product recommendations provided through augmented reality? How can the development of the user's preferences be supported by augmented reality enhanced product displays? Does the presence of a physical product serve as a cognitive anchor for selecting among online products? So to address these questions, we have performed a small user study that unfortunately had to be limited in size and scope due to physical proximity being restricted because of the COVID-19 pandemic. But in any case, 10 participants took part in it, 9 of them with strong technical background. 3 real vacuum cleaners were used, together with a database with 100 other products for generating recommendations. Participants were first introduced to the system, and then they were asked to solve 2 scenarios where they were given several requirements and had to find a suitable vacuum cleaner. The final choice could either be one of the physically present ones or an item found by using the recommending functionality. Participants had to fill a 3-item long questionnaire between tasks addressing their final decision and the relevance of the presence of physical items. And by the end of the session, they also answered the rescue items by Puetal and some other system-related questions. Now, jumping directly into the results, the rescue items were rated positively in general, particularly those regarding the novelty and diversity of the recommendations, the ease of use of the system, and the use intention, although the explanation of the recommendations seemed to be the system's biggest flaw. For the system-related items, the highest scores were given to the preference of the system over a more traditional medium and use intention, but the novelty of using a head-mounted display may have had an impact on these results. Closely behind are the items that deal with the helpfulness of physical products, while attribute exploration seemed to be the main issue for most users. The results of the between tasks questionnaire reinforce the helpfulness of physical products during the process, And even if not with that conviction, participants also showed confidence in their final choice to fulfill the given criteria. The empirical data shows that even though users were quicker in solving the second task, features like critiquing, selecting attributes, and reading their descriptions were used more often too, suggesting that they were found useful to accomplish the given tasks. However, it also indicates a learning factor supported by most participants affirming that they felt able to use the system competently only after having completed the first task. With respect to how users made a final choice, when solving a task, all participants focused on some physical products and their recommendations while completely ignoring those physical ones that they thought were not suitable. And by doing so, participants seemed to filter the digital space intuitively. Lastly, for both tasks, digital items were chosen way more often than the physically present ones, which is interesting because they generally showed confidence in their final choice despite of it. So coming back to our research questions, the recommender systems was positively rated and perceived as useful and intuitive. Physical products were regarded as helpful for forming an opinion of the ones available only in digital form, and the selection and exploration of products was influenced by the presence of physical items, which could be a sign of anchoring effects. However, caution is required when interpreting these findings due to the various limitations of the study, such as that participants might not be a representative sample due to the number and technical background, the limited number of physical products, the task scenarios also limited the development of user preferences, or the impact that using a head-mounted display may have had in the results. But altogether, we still believe that there is enough evidence to at least consider this to be a viable approach worth to be further explored. So future work will focus on consolidating the results presented here. We also aim to get a deeper understanding of preference construction in a hybrid physical online setting, and to provide more opportunities for users to experience digital products through physical ones. Finally, we would like to study new combinations of appearance and function-based recommendations and how different clients react to them. So this concludes my presentations. Thank you very much for listening. And if
Thank
there
you
is
very
any,
much.
Yep.
So we have already a question from Sami, who was wondering, can this be used for products from different stores or different data sources, so heterogeneous data sources?
Yes, I guess that could be possible, yes. That you can see digital products that are in a different store, yes, I don't see why not.
But you had a static data source, I guess, in this particular instance, right?
Pardon?
But you had a fixed catalog.
Yeah.
In this case,
yes.
it was homogeneous, but hypothetically it could be. And a question from Bob: why you think that people pick the digital products more often than the physical ones?
Well, probably because there were more variety, so they had more products to choose from, and probably some of them were more fitting for the tasks. This is a limitation of the study, that probably we have had more physical products, these numbers may have changed.
So final question from me, but if I could also ask you to stop sharing your screen so the next speaker can share theirs. Why do you think there was a lower score for the explanations?
Yeah, well, admittedly, there is no real explanation of why the digital items are being recommended, besides being attached to a physical product and being modified after critiquing an attribute. So it is up to the user to notice why they are modified or for what reason they appear where they appear, I guess.
Yeah. Well, thank you very much. And it's an exciting application. Maybe in the future we'll see more augmented reality stores when physical space is limited. And I introduce now Panagiotis, who is going to be talking about video recommendations. So what should we watch next?
Hi, my name is Panagiotis Symeonidis. I'm an assistant professor at Free University of Bolzano. And this work is the result of our 3-year collaboration with the UTV company, which operates in the province of Alto Adige in North Italy. I want to thank all co-authors Andreas, Dmitry, Philip, Daniel, Andreas, Ludovik, and Markus for this valuable contribution. You see the outline of our work, of our presentation. We will present our approach, and in the end, we will see some lessons learned based on our offline and online experiments. UTV supports users to record high-quality German television programs of their choice and view them whenever they want. So our problem is defined as follows. Given the current user session, what videos should we recommend to the user next? And the provider wants to engage the user more time in the website for reasons of advertisement and for fulfilling his viewing desires. Of course, there are several challenges, like the lifespan of video, which is short, the short user sessions, and the fact that the user sessions are anonymous, and the fact that the individual and public interest evolves fast over time. In this work, since this was an industrial project, we used well-known as comparison partners, well-known approaches in the area of session-based recommendations. So we used the session KNN algorithm, the GRU4Egg, the algorithm from Google, which was proposed in IUI in 2010, and the well-known item-based collaborative filtering algorithm. The heart of our approach is a Markov chain, which is a stochastic process of possible events that satisfies the Markov property. And here I will present a motivating example of our recommendation system. So in a real system, there is a server who logs the interactions of users with the items. So for every user session, we keep track of the items that are clicked. For example, here in session 7, we can, which is still open, and it is running for user 2, we can see that items I2 and I3 of session 7 can be matched in order to make item recommendations to user U2. Of course, there is also a sliding time window which should be considered in order to validate the user's clicks based on the time that they happened. And these are the things that we consider in our work. The system is composed of two main procedures. The first is the transition probability matrix creation. So given a user session, SN, where IM is the last item in this session, we define the score for a recommendable item J as follows. The right-hand side of this equation counts how many times user has viewed item J immediately after viewing item IM, and also the normalization term transforms the absolute count into a relative transition probability. So in our running example, we can compute the relevance between item 4 and item 6 based on this equation as 0.5. The second step of our approach is a recommendation list creation. As can be seen here, for user U, we can compute the score for a candidate item J by using these two functions, where the function TPM returns the similarity score for items I and J based on the Markov chain-based transition probability matrix, whereas the second function, the 1 bolt, is an indicator function which is equal to 1 if the item J is present within the k nearest neighbors of item I and 0 otherwise. So our approach consists of two modules. The first is the profile updater, where we keep track of the information and the logs of the log history of users, and we discard old information. And the second module is the recommender module, where we use the click history of the user in order to make recommendations. So this was an industrial project, and we collaborated with the company for over 3 years. And in the first phase, we performed offline experiments. We had this on May 2018 for 2 weeks, and as can be seen here on the left bottom figure, 50% of user sessions are in the offline dataset have only one video interaction. So this is what was the recommender systems of the company in 2018 when we collect this offline data. And as can be seen on the bottom right figure, in June 2019, users interact with 2 videos before leaving the service. So as can be seen here, we have managed to increase the length of the user visit with a factor of 2. The interactions per session initially were 3.6, where in the end, in the online evaluation, we had 7.24. Another important thing in our evaluation was to identify how big should be the size of the future horizon. So in the top left figure, we are able to predict better, as can be seen here, when we are trying to predict the next 12 hours. So this was very important for us to identify what would be the future horizon of our predictions. Whereas another important issue was to identify how far back into the past we should exploit data from. And as can be seen from the bottom right figure, when the window size, the time window size is bigger than 18, the precision drops, which means that not all the past data is valuable for our recommendations. So we compare our Markov chain-based transition probability matrix with other well-known methods like the GRU4egg, the session KNN algorithm, the item-based collaborative filtering. And as can be seen here, the Markov chain transition probability matrix were able to capture the notion of recency of users' interest and to capture the short-term preferences of users. Whereas the other methods couldn't capture the latent associations among items within a session. So this was the offline evaluation. And in the next step, we performed an online experiment. When a user or a UTV user logged into the system and visited the website, we recommended to him TV programs. So here we have 2 algorithms based on the previous experiment. The control group is the item-based collaborative filtering algorithm, whereas the test group is the transition probability matrix. And as can be seen here, we compute the CTR, which is the click-through rate of the recommended videos, which counts the number of clicks on the recommended videos every time the user visits the UTV website. And as can be seen, the CTR in the test group is clearly higher than the CTR in the control group. And we have improved the CTR upon the pre-existing collaborative filtering item-based collaborative filtering method by 93.61%. So this was something that when it was reported to us by the company, we were very happy. And this is like the experiments were performed in the level of the company, and we have given the algorithm to run the experiments. So, what were the lessons learned? The first thing that I would like to highlight is that it is very important to start working with not static train test splits evaluation protocols, but we should keep working with many train test splits, time-oriented train test splits, in order to be more relevant to what is happening in reality. The other thing is that maybe with this intra-session Markov chain, we were able to capture the short-term user preference, but of course, we could try to capture the long-term preference also. And another thing is that we should also try to work and run experiments with other state-of-the-art methods. Another important thing of our...
I'm sorry, we're kind of close to the end of the time here.
This is the last slide. Yeah, this is the last slide of my presentation. So, as can be seen here, and I will just say that the last bullet, it is very important to improve predictions, and we need to, in order to improve prediction, we need to identify first the size of the future prediction horizon, and also the size of the sliding time window, which processes and validates the past data. So this is the presentation, and I would be glad to answer your questions.
Thank you very much. And there's a lot of movement here in the question channel that I'm keen to make sure that we get answered. So one question from Carol: how does the solution deal with series or videos that are non-follow-up, somehow connected?
I know that the platform, the UTV.D platform, supports series, TV series. So this is also in the, it is recommended as TV shows or series, and we don't see it as something different. Probably the algorithm works also for providing, let's say, recommendations of series. But of course, if a user has seen some episodes, you will probably be recommended to see the next, I guess. So I don't think that there is something that differentiates this domain.
And then another question from David. As far as I understood, the proposed model updates the Markov chain in real time. Were the item models for the baseline algorithm also updated in real time for fair comparison?
Yeah, this is something that it is followed because we followed the exact procedure which is recommended in the IUI 2010 paper of Google. And so the item-based collaborative filtering algorithm runs on it is updated online. So it is updated and it is based on this item co-visitation procedure. Whenever an item is clicked after another item, this is an update to the item similarity matrix.
This answers also the question from Allegra. I have a nice question from Mohit about the catalog. So is the catalog rich enough to capture long-term interests, or do we have user history of sufficient length to capture that? Obviously, it's session-based, so this might be more tricky.
Well, I know that this platform has a lot of subscribers. Over 1 month, it's more than 100,000, as I remember. So there is a lot of data there. So probably what we need in order to capture the long-term preference of users is except trying to identify the connection between items inside a session. Maybe we should also try to infer the inter-session interactions of items. So in case that we don't have enough data about users inside the session, maybe a user just click one item, maybe we could identify other interactions from older sessions in order to find associations and relevancies.
Thank you very much for the nice Q&A. Again, please continue it on Wova. If I may ask you to stop sharing the slides so that Markus could share his. That's our next speaker who will be speaking about also a very important application domain, jobs, and something that is close to my heart as a professor, jobs for students. Just so you know, you're still muted, Markus. There we go.
I think everything works now. So welcome to the industry talk on the heterogeneous information needs in the job domain, a unified platform for student career. My name is Markus, data scientist at Telto. And in this talk, I'm going to share our experiences with solving the recommendation problem for university students. Specifically, I'm going to walk you through multiple considerations when developing a platform for students and how we at Telto tackle those problems. So let's first consider the job market from a recommender system's perspective. It's a difficult environment due to multiple factors. First, it is a multi-stakeholder system where the interest of both the employers and the employees needs to be balanced. Additionally, the job market is very competitive, as only the best candidate or the best company will be chosen by either side, respectively. As such, it can be seen as a matchmaking problem, where both parties must be satisfied for a successful match. Users on such platforms perform a low amount of interactions that can be used for training. Moreover, users tend to leave the platform after they found a matching job altogether. Due to this, it is important to consider the cold start problem, which is even more apparent. At Telto, we personalize the various aspects of the platform to overcome those hurdles, starting from the initial page. Telto is an Austrian career platform specifically tailored towards students and graduates. The platform itself is optimized for both desktop and mobile view. The latter is important as mobile applications appeal more to the younger generation. As seen on the left, we provide personalized job postings for users when they search for a job. And on the right, you see also cross-entity recommendations, where we recommend suitable articles based on the content of a given job posting. We found that our users, which are primarily students, have very different information needs. To satisfy those needs, we provide different types of content on our platform. Specifically, we provide job postings, company profiles, and career-related articles. Each type serves a different purpose and is of different relevance depending on the study progression. At the beginning of their studies, students search for part-time jobs and study specific career information. But when nearing graduation, their focus shifts towards relevant company information and full-time jobs. Additionally, we also need to deal with a periodically shifting demand as a result of the academic year, and handling both logged-in and anonymous users at the same time. Our solution uses a hybrid recommender system, which allows us to seamlessly integrate multiple algorithms into a platform for different use cases. For instance, we employ recommendations at multiple different locations, such as the main view and the sidebar. We employ a hybrid model that consists of well-established approaches, like collaborative filtering and content-based filtering. But we also use more sophisticated methods to create embeddings, like doc2vec and autoencoders. Our system is built upon a microservice architecture and uses the Apache Solr search engine, which allows us efficient retrieval and recommendations in real time. Here we see an example where we use the last interaction to find similar embeddings using doc2vec. Additionally, we improve the algorithms by incorporating cognitive-inspired recommendation approaches. For instance, one approach shown on the right uses a psychological model from the human memory theory. We use it to create weighted embeddings that consider the recency and frequency of interactions of the user's history, instead of using only on the most recent item, as seen on the left. We also continuously perform A/B tests of our algorithms. Here, for instance, we saw that by using the base level learning equation, we were able to improve the popularly used collaborative filtering for homepage recommendations. But on the details page, things are a little bit different. Here we saw that just considering the last item of the user's history gave us much better results. We investigated this by tuning the BLL equation and saw that the effects of recency have a greater influence for the user choice in context-dependent settings, as indicated by the higher time decay parameter D. As already said, we also focus on anonymous users. In this session-based scenario, we use autoencoders to infer embeddings for a particular session. This is then used in a KNN manner. If we want to know more about the specifics, we just published a UMUI journal paper on this. While all of these provide effective recommendations, it takes a lot of fine-tuning for each use case to work well. Therefore, we were looking for a more generalized solution that can tackle the various different information needs, especially one that allows us to generate suitable cross-entity recommendations. In our latest effort, we adopted an approach called Item Concept Embeddings, or ICE, for recommendations. The idea is to create an information network consisting of both items and words, shown on the left, and transform them into the same latent space. As you see on the example on the right, from the original authors, the words Japan and Godzilla appear close to Godzilla movies. In our case, we first pre-train word-to-vec models using the user and item vocabulary. For example, with the top TF-IDF words from the job description. Then we create a heterogeneous information network consisting of items and words. We extract and link the concept words for each item. We then link each word to similar words, both from the item, shown in red, but also from words belonging to the user profile, shown in blue. We then learn the final embeddings of both items and words on the graph. For more information on the training procedure, refer to the ICE paper. Our training procedure thus considers the network topology as well as the textual content. We store this once again in Apache Solr to allow for real-time recommendation generation and retrieval. Now, with all this set up, we can utilize the network embeddings for 3 scenarios. Item to item, which allows us to recommend similar items. User to item, to create a personalized experience. And also query to item, where the input is a word. Thus, it can also be used for improving the search experience. While the example shows the procedure for job, we can use it regardless of the entity type. The important part is the overlap of the user vocabulary, which we built from user-created CVs on our platform. While the main focus of our approach is to provide cross-entity recommendations, we also found other use cases for it. This is true especially in terms of explainability. Since the model uses text as an integral feature, it makes it simple to show explanations of recommendations generated with ICE. For instance, if a job requires Scala and the user has Kotlin experience, we see that Java is the common denominator that is linked to both those concepts and can be shown as an explanation. Additionally, it also allows for several easy-to-implement use cases. For instance, we can automatically generate complete content pages for suitable terms like deep learning, as seen on the left, or use it to extract the concept from a word from a job posting to promote email subscriptions, as shown on the right. This work is the result of a research project comprising the startup parent company, Moshpit, the Node Center, and the Graz University of Technology. Thank you for your attention, and I hope you enjoyed this presentation.
Thank you for this nice talk, Markus. It's not an easy job to match these heterogeneous requirements of job seekers and employers, indeed. And we have a question from Zeno. What are the criteria that you mentioned about the middle of the talk that you said were accuracy and beyond accuracy metrics?
Sorry, could you repeat it regarding?
So around the middle of the talk, you mentioned accuracy and beyond accuracy metrics for evaluating your methods.
Yeah, so,
which one specifically did you look at?
This is so we, like I said, we recently published a UI paper where we evaluate this in greater details. But one thing to keep in mind when we look at it from the needs perspective, we need to consider the beyond accuracy metrics, since we need to provide novel recommendations. Otherwise, you have, if everyone applies to only popularly used items, then it's not satisfying for both parties, since the job seekers don't get jobs that don't apply to jobs where they have a high success rate of being accepted. And on the other side, some companies might not get any recommendations, while other companies might get a lot of recommendations and get flooded.
So were you able to measure this? This is actually a question for Shu Jun, right? It's indeed a multi-stakeholder problem, not just for the job seekers, but also for the employers. So we're able to measure the satisfaction or the accuracy for employers.
No, so we did not directly measure it, but when we performed online tests, we saw that it's actually related. So we have, so when we did a simulation, for instance, on the cognitive inspired recommendation approaches, we saw that when we only optimized for accuracy, then these models perform worse than we considered both, looked at models that have both a high accuracy and also a high novelty or beyond accuracy measures.
And a really nice... So then we also had a very nice question from Allegra. Did you take any steps to ensure fairness in job recommendations? She gives an example. It's known that women apply less to jobs with stronger requirements and simply might not click on reach jobs as much as men, and then optimizing for CTR click-through rate might lead to bias. So have you looked at fairness?
Not yet. As you might seen from the talk, there are many different things that you actually need to optimize on such a platform. And also, since the users are also very different, it's, I guess, the metric fairness would also mean something different for different users.
Then thank you for the nice talk. I again encourage to look at the questions on WOVA. And I welcome our last speaker of the session, Balazs, who will be talking about the balance between relevance and discovery, and particularly in the context of the IKEA app.
Hi, do you think that you are unique? I think you are. Why do I say this? Because in this conference, I have seen many presentations, and most of the people tend to use similar slides. Same software, same style, same fonts. Why is this? Because the slide creator software tend to recommend us the same things, and we are lazy enough to click on some of the first options. The recommender system influences us. We can look at recommender systems as influencer systems. Let's take a classical collaborative filtering approach as an example. In this case, the model is trained on user behavior data, so the users influence the model. And the model gives recommendations to the users, and they are clicking on some of the first options. So the model also influences the users. These two things amplify each other. Let's imagine that this recommender can potentially recommend 3 images, image A, image B, and the third image with the small chairs on top of each other. But in practice, it always recommends image A or image B. It never recommends the third image with the small chairs. So it continuously recommending image A and image B, and it becomes a pattern in the data. And the recommender exploits this pattern and never explores the third image with the small chairs. If it would, maybe this small images, this image with the small chairs would perform better than image A or image B. But we never know it because it just doesn't explore it. And this is the shortcoming of classical recommendations. And I'm happy that Ricardo in his keynote speech also talked about this problem. We keep addressing this problem in the IKEA app. Let me tell you more about this IKEA app. I'm Balázs Tóth, data scientist at IKEA. I work on a new product that is called Inspiration Feed. It is in the IKEA app and also in the web, but now I'm talking about the app. You can see an example of the Inspiration Feed on the right side of my slide. It consists of inspirational or shoppable images. One inspirational image consists of a set of IKEA products displayed in an atmospheric setting. We serve around 50 million recommendations daily. With such a robust system, it's easy to get feedback what is working in recommendation and what is not. IKEA tries to transfer its home furnishing knowledge from the stores to the app and the web. And the Inspiration Feed is one of these initiatives that tries to contribute to this mission. It is one of the first things that the customers see on the IKEA app. So it needs to be explorative like the IKEA stores. I can compare it to recommendations in a product page. In a product page, we know more about the intention of the customers, and we display recommendations that are connected to that specific product. Here, the feed needs to be more explorative, but it also needs to be relevant, otherwise the customers lose interest. So it needs to be relevant, and it needs to have the element of surprise. To achieve this, we need to balance relevancy and discovery. So we have two problems that we're trying to solve here. First, we want to avoid the bias in the recommender systems that I talked about in the introduction, and we want to balance relevancy and discovery in a good way. To achieve this, we use contextual bandits. More precisely, we use contextual bandits with batch learning from logged bandit feedback. We use counterfactual learning, and we make use of the counterfactual risk minimization principle. In our setup, the context is user clickstream history. An action is when a recommender displays an image, and reward is generated when a user clicks on an image. Our policy is neural networks that uses embeddings of the input features. We retrain this model daily. And how do we do this exploration? That's the key part. We do it with the help of logged propensity scores. So the idea is if an image gets low propensity scores, but got clicked at the same time, we put more weight on it to boost it, to explore its potentials. So it's a targeted exploration. And the intuition is coming from the statistic technique called inverse propensity weighting. Inverse propensity weighting is used in experiments when some element of the population is underrepresented. For example, men above 100. And in this case, we put more weight on the underrepresented samples to balance the underrepresentation. But how do we incorporate this to the training? We do it in the loss function. It's a custom loss function, and it is the heart of this approach. We are optimizing the expectation of reward under a new policy. Let me go through the notation. Delta is the reward function. It returns 1 if there is a click, 0 otherwise. X is the context, is the clickstream history. Y is the action, displaying an inspiration image, and pi is the policy, the model. So pi theta is the new model, and pi 0 is the old policy. It's coming from the logs. So first, we compute the new propensity scores with the new model, divided by the old propensity scores, and then multiply this with the reward function, which gives 1 if there is a click, 0 otherwise. So we're only dealing with the clicks. After this, we're taking the average of it and maximize it. In practice, we're taking the negative of it and minimize it, since we are working with gradient descent. Let me show you as illustration how this recommender uses exploration in practice. So here in this example, the context is viewing a chair. So in this video, you will see that if a customer clicks on the chair, after which kind of recommendations that customer is going to get. And you will see that we retrain the model daily. So it does the exploration every day, and it learns from the exploration. And it improves. So this is the images that you get in the first day of your clicking this chair. Second day, even you see that there are more images with that specific chair because the system is learning. I wanted to illustrate the dynamicity of this approach. I'm proud that we have built a powerful recommender system for the IKEA app. We ran an A/B test, where the A version was a classical collaborative filtering approach, and the B version were contextual bandits. We ran the A/B test for a week. There were around 1 million unique visitors involved in the test, and we ran the test in the 6 biggest IKEA markets, in the 6 countries when IKEA has the biggest markets. And the contextual bandits showed 20% increase in click-through rate. And in our case, click-through rate was the measure of success. The shortcoming of this approach that it only explores images that were clicked. So it can be a problem with the cold start of inspiration images. To solve this issue, we have another panel where only the new inspirational images are displayed. So initially, we assign some propensity scores to these images, and as they get clicked in this new panel, they naturally blend into the training data. We want to experiment with the loss function, and among others, we want to use images as input to the neural networks. I summarize my talk. Exploration is essential for a good recommender. And if there is one message that you can take away with you, I hope that this is it. We used contextual bandits in the IKEA app, and it improved recommendation quality and variety. We ran an A/B test, and it showed 20% increase in click-through rate for the contextual bandits. Thank you for your attention. We can proceed to the questions.
Thank you for the very nice presentation, Palas. I think it's very rare that we see such an increase. 20% click-through rate is quite astounding. So a question here from Justin. Did you use the item embeddings through the click behavior, or are they also a function of item content and images?
Click behavior. Actually, we tested also with some product metadata, but in the end, we didn't include it in the first version. And actually, it's a coming A/B test that we want to try out with product metadata. And we hope that it will help for the cold start or for users that doesn't have so long click history.
So I'm going to be a bit cheeky and ask a question of my own here. For learning the policy, it seems like it's individual by user, if I'm understanding correctly. Did you look at how different it was between different users, so that some users that there's more of a policy to explore or exploit?
So it's not different by user, actually.
Okay.
So like if you click on the same items as another person, you get the same recommendations. So like if you click on this chair and only in this chair, and another person is also clicking on this chair and that specific chair, then you get the same recommendations.
Right. Makes sense.
So it's only improving day by day when we retrain the model on the batches. So it's not not improving online. So it's the batch phase that is doing the exploration. it's a conservative approach.
Mm-hmm. Thank you. Sino asks, did you measure the long-term user engagement as well as CTR?
No, but we are going to do that.
Thanks. Sandra asks, the 20% increase that you saw, was it across 6 markets? And was there any differences in the different markets?
Yes, so like it was globally 20%, and in some countries was higher. I think Sweden was the highest, like around 23, and some other was like 18.
Question from Vinny. Did you have any control mechanisms to avoid overrepresentation of the same category? So just showing living room versus bouncing different kinds of images?
No, it's coming also to
so
experiment.
You see that happening.
So it will be a following A/B test. And we also want to do exploration that is not just targeted, but more random.
Question from Fernando. Did you try your solution in an offline scenario?
Yes. So we had also offline evaluation, and mostly we looked at top key accuracy. And actually it showed quite high top key accuracy from the beginning. So it was around 40%, like the top 10 accuracy was around 40%. But here we are optimizing for click-through rate. So it's a good initial metric, but afterwards we don't care so much about it because we care about the click-through rate. And this approach is optimized directly for click-through rate, not for the offline metric.
Thanks. Question from Norman. Is it possible that running the A/B tests for only a week led users to click more on the B, the novelty recommendations, because they were different from what they were usually seeing in A? And does this novelty eventually wear off?
So the question is, if I understand, if we run the A/B test for one more week, maybe it would change the results.
Mm-hmm.
Yes, we don't know that.
Interesting to see.
But actually, I don't think so.
I think we didn't ask.
We continuously monitoring it, and it shows great results. So it's not an A/B test, but we are just monitoring it.
Nice. I think we didn't ask this one from Zeno yet. Is it right that the loss function only considers positive events, so clicks, and non-clicks are ignored?
That's correct. So we are only training on the clicks. So that's why I said that it's a targeted exploration. So it has its limits, as I said. So it doesn't explore the images that never got clicked.
Nice. A few people are asking Jean-Michel, what was the baseline model? So what was the model that was compared?
So it was
a bandit.
I tried to describe it. So it's a collaborative filtering approach. So it computed the similarities among products based on session history. And then there was a matrix between inspirational images and products. And the similarity metrics were used in the matrix. And then there were some computation afterwards to find the best inspiration images, to find the best ranking.
And maybe a last question from Shangfan. Do you take the number of minutes that the products were viewed into consideration for engagement?
No, but it's a good question. It's a nice idea.
So thank you again for the very nice talk. Thanks everyone for being engaged in the Q&A. Many more questions than we managed to cover, I think, for all the speakers. So please do continue to have your dialogues on Whova. And after this session, there are social events. There is a second round of the women's meetup, but there are also posters coming up. So please do enjoy the rest of your conference, and we will see you in the other sessions.